Okay, good morning and welcome back to Modern Physics, Session 6. I hope all of you have gone through previous two lectures on vector atom model. Now we will extend our understanding on vector atom model to get a better picture of the distribution of electrons within the atom using quantum numbers and then briefly explain the production of atomic spectra. While analyzing Schrodinger equation for hydrogen atom in quantum mechanics, the wave functions are determined by the values of three quantum numbers n, L and ml. In Bohr atom model, in our previous lectures we had seen the energy of electron in various orbits of hydrogen atom may be expressed as minus mz square e raised to 4 by 8 epsilon 0 square n square h square, from which we got a final result minus 13.6 by n square electron volt. That is, the energy of electron is determined purely by principal quantum number n. But in the last session, we had seen that magnitude of orbital angular momentum of the electron is decided by the orbital angular momentum quantum number L, and the component of orbital angular momentum in a specified axis direction is determined by magnetic quantum number ml. Even in a classical system like orbiting satellite, energy of the satellite depends on the average distance between the satellite and the center of the earth, or it does not depend on whether the orbit is circular, which is having reasonably higher angular momentum, or elliptical, which is having comparatively smaller angular momentum. That is, that distance is the parameter, not the angular momentum. So in the same way, it has been established that energy of a hydrogen atom does not depend on the orbital angular momentum. That is, energy of an atom does not depend on the values of L or ml, which means for each energy level En described by Bohr atom model, there will be more than one distinct state having same energy but different quantum numbers. Okay, this existence of more than one distinct state with the same energy is what we call degeneracy, and it has no counterpart or no such idea in Bohr atom model. So vector atom model introduced this idea of degeneracy, and which successfully explained many of the behaviors exhibited by the atom, particularly the complex atomic spectra and various phenomena like Zeeman effect, Stark effect, etc. So today we will analyze various quantum numbers which we had seen in the discussion of vector atom model to establish the distribution of electrons within the atom. So we call it electronic configuration. So we will specify, specially touch upon maybe a point given in the syllabus, that is Paulie's exclusion principle. So Paulie's exclusion principle helps us to account for the distribution of electrons within the atom. So we call it electronic configuration. We will see in the following slides. Basically, electrons are to be distributed in various subshells, and the distribution of electrons in subshells in an atom is known as electronic configuration. Subshells are represented in terms of orbital angular momentum quantum number L. Orbital angular momentum quantum number L can take values from 0 to n minus 1. We call it 0, 1, 2, 3, etc. n minus 1, and are represented using spectroscopic notations S, P, D, F, G, H, like that. So value of principal quantum number n is written as a prefix to the letter representing its L value. You have come across 1s2, 2s2, etc. So number of electrons having the same n and L value is represented by an index or power written at the upper right of the letter representing the L value. So in 1s2, so 1 is principal quantum number, S is that is subshell, and 2 is the number of electron in that subshell. So that is 1s2, 2s2, 2p6. So we should understand this distribution of electrons in detail. An electron in an atom is associated with various quantized vectors: orbital angular momentum, spin angular momentum, then total angular momentum. Also associated magnetic moments or magnetic quantum numbers. When we study or visualize an atom, the quantized vectors of the electrons within the atom are to be coupled to represent the atom as a whole. Or so to say, to represent the atom in terms of the effective quantized vectors. There comes the importance of coupling or mixing, which we will analyze in detail in the next following session. So today we will be focusing our attention to distribution of electrons. So in an atom, the state of an electron is specified in terms of 4 quantum numbers. We call them N, L, Ml and Ms. And the number of electrons or electron states should be consistent with an important rule or principle which we call Paulie's exclusion principle, which states that no 2 electrons in an atom can have all the 4 quantum numbers identical. This N, L, Ml and Ms cannot be same for any 2 electron. If a second electron is coming with identical quantum number, it will be excluded. It implies that each electron in an atom must have a different set of quantum numbers N, L, Ml and Ms. If 2 electrons have all their quantum numbers identical, then one of these 2 electrons would be excluded from entering into the constitution of the atom. And hence the name, this exclusion principle. So the number of electron states or state of an electron in an atom is described by 4 quantum numbers N, L, Ml, Ms. 2 electrons cannot have same quantum states. So to understand this concept, we can analyze a few situations here. Let's start with K shell. You all know that K shell can accommodate 2 electrons, or only 2 electron states are available in K shell, which is the innermost shell of an atom. For K shell, the principal quantum number is N is equal to 1, and the orbital quantum number L can take values from 0 to n minus 1. So only one value for L, which is L is equal to 0. No magnetic orbital quantum number Ml or magnetic orbital quantum number can take values from minus L to plus L in steps of 1. So in K shell, L is equal to 0, Ml is also 0. So in vector atom model, we have seen that Ms always takes values plus half and minus half. So in K shell, there are 2 states. First one is defined by quantum numbers N is equal to 1, L is equal to 0, Ml is equal to 0, Ms is equal to plus half. And second state or electron is defined by N is equal to 1, L is equal to 0, Ml is equal to 0 and Ms is equal to minus half. So K shell can accommodate only maximum of 2 electrons. And if you think of a third electron in K shell, its quantum number will be one of the above 2 and hence will be excluded. So this is what Paulie's exclusion principle. So Paulie's exclusion principle is a consequence of vector atom model. So this is an extension of vector atom model. Now we will elaborate Paulie's exclusion principle to calculate the number of electron states in other shells as well. So here this slide, it is L shell is shown. For L shell, principal quantum number N is equal to 2. Corresponding orbital quantum number L is, that is, it can take values from 0 to n minus 1. So L can have values here 0 or 1, 0 and 1. That is, L is equal to 0, we call it S subshell, and L is equal to 1, we call it P subshell. Now we can analyze S subshell and P subshell separately. So first one, S subshell. So N is equal to 2, L is equal to 0. So naturally Ml is also 0 and Ms can have 2 values, which we have seen also in K shell. So there will be 2 quantum states possible with S subshell of L shell. So it accommodates 2 electrons. Now P subshell of L shell. principal quantum number is again n is equal to 2, and orbital quantum number L is different, that is L is equal to 1, and the corresponding magnetic orbital quantum number is ML can take values ML minus 1, ML 0 and ML plus 1. For ML is equal to minus 1, again there will be two states corresponding to MS plus half and MS minus half. Then two quantum states for ML is equal to 0 with MS plus half and minus half, and two more states corresponding to ML is equal to minus 1 with MS plus half and minus half. So it shows there are 6 quantum states associated with P subshell of L shell. So 2 quantum states associated with S subshell of L shell and 6 quantum states associated with P subshell of L shell. So total of 8 electrons can be accommodated in L shell, or there are 8 electron states available in L shell, which are shown in the slide. You may pause here and try to find the number of electrons and subshells in M shell and N shell as well. So for M shell, principal quantum number N is equal to 3. Then L is equal to 0, 1 and 2. And ML for L is equal to 0 is 0. For L is equal to 1, ML can have values minus 1, 0 and plus 1. And for L is equal to 2, ML can have values minus 2, minus 1, 0, plus 1 and plus 2. For each of the ML values, there will be 2 quantum states corresponding to MS plus half and MS minus half, which make a total of 18 quantum states or electrons. Similarly, if you work out that is for N shell, you can show that there are 32 electrons. So for K shell, N is equal to 1, it is having one subshell, that is S subshell, and 2 electrons. For L shell, N is equal to 2, it has got 2 subshells, that is S and P, and 8 electrons. For M shell, N is equal to 3, there are 3 subshells, that is S, P and D, and 18 electrons. So for N shell, principal quantum number N is equal to 4, so there are 4 subshells and number of electrons will be 32. That is, if you generalize, you can see in the nth shell there are n subshells corresponding to the values of L, that is 0, 1, 2, etc. up to n minus 1, right, the values of L. So number of subshells in a shell is nothing but the number of values of orbital quantum number L. Not the value of L, but the number of L values or number of values of L. How many L values? That is 0 to n minus 1 values of L, which fix the number of subshells in a shell. You just think and understand this discussion. Maybe pause for a minute and analyze whether you get this picture here. There is another relation which you can see from the number of electrons in various subshells. We will see. In K shell, N is equal to 1, L is equal to 0, and there is one subshell. So here it is not the value of L, but number of values of L. If it was value of L in K shell, L is equal to 0. There will not be any subshell. But here number of values of L is 1, that is the value is 0. So number of values of L is 1 and the number of subshells is also 1, which is S subshell. In L shell, N is equal to 2, L is equal to 0, 1. Therefore total number of electrons is 8, of which 2 are in S subshell and 6 are in P subshell. P subshell corresponds to L is equal to 1 and is having 6 electrons. Right? Similarly for M shell, N is equal to 3, L is 0, 1 and 2, and subshells are S, P and D. So there will be 18 electrons, 2 electrons in S shell, 6 electrons in L is equal to 1, that is P subshell, and 10 electrons in L is equal to 2 or D subshell. If you proceed like that, you can try 2 into 2L plus 1 for various subshells. It is shown in the slide. For S orbital or S subshell, L is equal to 0. So 2 into 0 plus 1, that is equal to 2 into 1, that is equal to 2. That is, there are 2 electrons in S subshell. For p orbital, L is equal to 1. So again you apply that equation, 2 into 12 plus 1, this 2 into, within bracket, 2 into 1 plus 1, that is 2 into 3 is equal to 6. That is matching. There are 6 electrons in p subshell. If you go for D, then L is equal to 2, then 2 into, within bracket, 2 into 2 plus 1, that is 2 into 5 is equal to 10. That is, there are 10 electrons in D subshell. Similarly, for F orbital, L is equal to 3, and you can calculate, you will get 40. Said there are 14 electrons in F subshell. Or in general, maximum number of electrons or electron states in a subshell with a given value of L is 2 into 12 plus 1. So you can try for any subshell. So many subshells you have come across S, P, D, F, G, H, etc. So you may pause and calculate number of electrons in other subshells like maybe G or H, etc. as well. So in G, if you work out, I think it will be 18. Try. Then another gradation you may note, for L is equal to 0, there are 2 electrons. L is equal to 1, there are 6 electrons. L is equal to 2, 10 electrons. L is equal to 3, 14 electrons. L is equal to 4, 18 electrons. Then next L is equal to 5, what do you expect? 22 electrons. Because see, there is a gradual increase. That is, number of electrons increase by 4 with every increase in L value. Right? You just check that slide, you can see it right end. Similarly, one more data we will analyze in connection with this number of electrons in a shell. We will see in the next slide. So this shows total number of electrons in a particular shell. Total number of electrons that can be accommodated in a shell with a principal quantum number n is equal to the sum of the electrons in the constituent n subshells. Right? Because there are n subshells for a shell with principal quantum number n. So a shell with principal quantum number L will have n subshells, and whatever is the total number of electrons in those subshells associated with the shell, that will be the total number of electrons in that shell. Clear? There are 2 into 12 plus 1 electrons in a subshell with orbital angular momentum L. And there are 0 to n minus 1 values of L, or number of subshells will be 0 to n minus 1. So mathematically, the number of electrons in a shell can be calculated using the expression summation L from 0 to n minus 1, 2 into 12 plus 1. That is equal to, the 2 is taken out, 2 into summation L is equal to 0 to n minus 1, 12 plus 1. When you work out, when you substitute the values of L is equal to 0 first, then 2 into 0 plus 1, that is 1. Then you can put L is equal to 1, then 2 into 1 plus 1, that is 3. So like that you can extend. All the terms can be included. And finally, if you work out, this will be equal to 2n square. Generally, we use the expression 2n square for calculating the number of electrons in a shell, and this table shows the number of electrons in various shells. So from our discussion so far, you must be able to give electronic configuration in atoms. A few simple examples are given. Orbital angular momentum quantum number L can take values from 0, 1 or 0 to n minus 1, 0, 1, 2, 3, etc. and the corresponding spectroscopic notations S, P, D, F, G, H, etc. Value of principal quantum number n is written as a prefix to the letter representing its L value. So 1 S, 2 P, something like that. Number of electrons having the same n and L values is represented by an index or power written at the upper right of the letter representing the L value. So that is 1s2, 2s2, 2p6, that's 6, that is power. So 2 electrons of a normal helium atom may be represented as 1s2. 8 electrons in oxygen atom may be represented as 1s2, 2s2, 2p4. 11 electrons in sodium can be represented as 1s2, 2s2, 2p6, 3s1. So this indicates that in helium there are 2 1s electrons, in oxygen there are 2 1s electrons, 2 2s electrons and 4 2p electrons. In sodium there are 2 1s electrons, 2 2s electrons, 6 2p electrons and 1 3s electron. So I suggest you to prepare a table showing 4 quantum numbers which fix the quantum states of an electron within an atom, that is n, l, ml and ms. So you may take values of n 1, 2, 3, 4 and 5 and give corresponding values of L, ml and ms and number of electrons in various subshells, their spectroscopic notation for those electrons, the number of electrons in various shells and subshells. So you may plot it on a sheet of paper and you can submit as a scanned copy, maybe as a response to the assignment. So this will give you a clear understanding on what we have discussed today. Okay, so then next that atomic spectra and etc. we will discuss in the next session. Thank you. Have a good time.